Hello, and welcome to the latest e-learning event from Petrol Industry News, sponsored by Teledyne Gas and Flame Detection. My name is Tom Lynch, and I'm a consultant editor for Petrol Industry News here at International LabMeet. Now, before we start, I would just like to go over some housekeeping. On your display, you will be able to see a questions panel. Please type and submit any questions in this area, and we will review as many as we can at the end of the presentation in our dedicated question and answer session. Any unanswered questions which we cannot cover in this session will be answered by email after the event. If you have any questions or technical problems with viewing or hearing today's session, please use the questions box to describe your issues, and our support team will respond to technical system questions instantly. Also, please make sure your internet speed is adequate and be aware that wireless connections may disrupt your session. Now, we are making this e-learning event available for on-demand review, and this will be on our website in 24 hours' time. In the petroleum and petrochemical industries, process safety is a critical activity which is always at the forefront of the minds of employees at all levels of the organisation. Obviously, fire and explosion are key hazards for these industries, and it is fitting today that our e-learning session focuses on some critical layers of protection which can be employed to manage such hazards and the resulting risks. Our topic today is safety, integrity levels and functional safety for gas and flame detection. And our expert in this area is Stephen B. Harrison, who is founder and managing director at SBH4 Consulting based in Germany. Stephen is an independent consultant with over 30 years' experience in a diverse range of industrial gases and their application, through working with both BOC in the UK and Linde Gas in Germany prior to becoming a consultant. So without further ado, I pass you over to Stephen to share his expertise in this area with us.
Tom, thank you so much for that introduction. Yes, this is Steve Harrison, and we'll be talking about safety, integrity levels, or SIL, and functional safety, specifically with an eye on gas and flame detection. And in addition to thanking Tom as our moderator today, I'd also like, of course, to thank Petrol Online for hosting the webinar, and our sponsor, Teledyne Gas and Flame Detection. Without their sponsorship, events like this wouldn't be possible. So thanks very much indeed to all of the hosts today. So perhaps you'll remember this image, this graphic, when you registered for the course, really just confirming this is what you've signed up for. And I hope that the agenda today will deliver on your expectations. So this is the agenda for today. We'll start by looking at some terminology related to SIL and functional safety, get some definitions under our belt. Then we'll look at some international standards, some ISO standards and some IEC standards with direct relevance to gas and flame detection and also functional safety. We'll look at some fit-for-purpose gas and flame detection system design. Now, what does fit-for-purpose mean? Not too much and not too little. And we'll look at some equipment, some gas and flame detection equipment that is SIL certified, let's say level 2, for example. And we'll take some examples from the Teledyne product range as we do that. And then finally, we'll look at some emerging applications for gas and flame detection equipment, perhaps with an eye on the hydrogen economy, for example. A very important slide. I hope you learned something very useful during this webinar, and that would be great. But please do bear in mind, this is no substitute for the work that you will need to do. Every system needs to be designed and configured according to the specific situation, and please bear in mind this course does not provide any specific advice to your situation. We simply don't know enough about what you're doing for this course to be specific to your needs. You will need to work on your own designs and your own HAZOPs and your own studies to confirm and validate that what you're doing is appropriate for your circumstances. So let's get on with it. Let's get started. Some terminology related to safety, integrity levels, and functional safety. Here are some definitions. The text here, by the way, on this slide is pulled directly from a white paper that Teledyne Gas and Flame Detection has made available recently related to functional safety SIL and gas and flame detection. And it gives us some very, very important definitions here. Safety integrity limits, or SIL. And they are a subset of what people refer to as functional safety, a very, very broad term. As an example, what we would want to say is that a safety function may wish to operate 90% of the time. The consequence of that is that it will not be operating for 7% of the time. A more reliable system, therefore a system with a higher safety integrity level, means that that safety function might be operating, for example, at 99% of the time, or conversely not operating for only 1% of the time. And this is a reduction in the risk level of a factor of 10, or 1 order of magnitude. And we would therefore say that the improved system would have a higher SIL rating of 1. So we move from 2 to 3, or from 3 to 4, or from 1 to 2, as we increase the system reliability by a factor of 10. So what is a safety function? Well, functional safety refers to the ability of a system to invoke a safety function. That's what it's all about. And a safety function might be something like an alarm, an audible or a visible alarm, a flashing red light, or a siren working in the factory. Another example, a safety function could initiate, for example, a firefighting pump. It could start the pump to make sure that the firefighting system is pressurized with water ready to be used. Not necessarily initiating water sprinklers, but simply starting the pump to make sure that the system is pressurized and ready. It could, of course, go one step further and initiate a sprinkler system. We could ask ourselves, what is the appropriate SIL rating? For any system that you're working with, maybe it's an LNG storage facility, maybe it's a refinery, maybe it's a simple petrol station. What is the appropriate SIL rating? Very, very good question. Well, if there's extremely high hazard associated with the process, such as a nuclear reactor, and especially the primary and secondary protection systems of a nuclear reactor, we would want those to operate at a very high SIL rating. Now, what does very high mean? It means 3 or 4. Even on the nuclear power plant, it may be appropriate, it may be fit for purpose, that other non-critical elements of a nuclear power plant may operate at SIL 1 or 2. And you can see in the table here what we mean about a risk reduction factor, or a probability of failure of that safety function on demand according to those various different SIL ratings. This whole concept of probability of failure on demand is really all about saying, if I need that thing to work, if I need my sprinkler system to come on, if I need that alarm to work and warn people, what are the chances of it actually working when I need it to? Or what are the chances that it will be broken? And we can think about some scientific terminology here related to probability of failures per hour. We could also, for example, express it as probability of failures per day or week or year. But in the context of SIL terminology, the probability of failures per hour, or the PFH, is the relevant terminology. So thinking back to what we've just been saying, SIL ratings are analogous with the reliability of a safety function control system. And bear in mind that a reliability of 99% means that it is not working 1% of the time. And when we were thinking about probability of failures on an hourly basis, daily basis, or weekly basis, let's just take that example. Within a year, the system might not be working for 3.5 days. And if those 3.5 days are all together, Monday, Tuesday, and Wednesday, that might be a completely unacceptable level of risk. That's 3 days that my system is completely unprotected. On the other hand, if the system is not available for 40 seconds every hour during an automated calibration or self-test routine, you may say that that risk is totally acceptable. It's only down for 40 seconds. It'll be up again very, very soon. And this is why we need to think about this concept of reliability and probability of failures on demand within an hourly context, so that we have some uniform definitions and understanding of how this system will be available to us to operate the safety function. I'm sure all of you, as operators or builders, constructors of petrochemical, petroleum processing, fossil fuel processing, energy facilities, will be quite aware that issues can escalate rapidly. From a small fire in an electrical switch box, we can end up with a whole terminal being damaged if we're not very, very careful. Things can escalate very, very quickly. And therefore, safety functions must be available when required. Or if the calibration and test routine is 40 seconds, okay, that might be acceptable because we know that that safety function will be available 40 seconds later to sound the alarm. And that flame that you see on the left-hand side within 40 seconds or 1 or 2 or 3 minutes can quickly escalate. So we really do need to have things available on demand. So that was some terminology related to safety, integrity levels, and functional safety, laying a platform for what we're going to talk about next. We're next going to look at some standards, some internationally relevant standards with relevance applying SIL and functional safety directly into the sphere of gas and flame detection. There are several bodies that have published international standards related to functional safety. The ISO, for example, IEC, and in the United States, the ANSI and ISA standards are widely recognized. Some of the examples on this slide are specifically related to functional safety. They may go on to say things about gas and flame detection, but here, the examples here are focused on the broad aspects of functional safety. The IEC 60079-29 group of standards is of particular relevance to safety integrity levels and functional safety for gas detection. In addition to those standards being relevant to SIL and functional safety, there are some specific documents within that family that go well beyond the focus of today, well beyond SIL and functional safety into a lot of other areas. For example, selection, installation, use, and maintenance. Furthermore, that group of standards is specifically focused on explosive mixtures, but those standards are also considered to be best practice for handling oxygen, which itself is not explosive, but leads to other gases becoming more explosive and more flammable, and also toxic gases, some of which, such as hydrogen sulfide, are indeed flammable, many of which are not. So it's a very, very wide-reaching and useful group of standards for anybody involved in gas and flame detection. And what I find very interesting in the standards is they assign responsibilities to the manufacturer of the equipment. For example, Teledyne Gas and Flame Detection as a manufacturer of gas and flame detection equipment. And also responsibilities are assigned to the operator, to the owner of that gas and flame detection equipment. And clearly Teledyne are well aware of their responsibilities and well aware of the standards that they need to conform to. And as operators, I'm sure you're also equally as responsible and equally aware of the standards that apply to you. Also, the installer of the system has various different responsibilities laid down in these standards also. So through the manufacturing of the equipment, its specification, its design, its installation, and also its use, there are various different standards and responsibilities that apply across that whole chain. And as an operator, one of the important things to be aware of are your responsibilities for maintenance of a system. It's absolutely essential that we buy the right equipment and it's installed properly, but once it's on our site, we also have an ongoing lifetime responsibility to make sure that it remains in good condition through a responsible maintenance program, which may, for example, include bump testing of gas detection equipment. This is an interesting aspect because as an operator, if you're looking to simplify your business model, then perhaps renting equipment or taking on a service contract, a maintenance contract through one of the gas and flame detection suppliers such as Teledyne may be something that is attractive to you. To make sure that you're focusing on running your refinery or running your storage terminal and allowing somebody else to look after this particular aspect of the operation. Fit for purpose gas and flame system design. We've seen that safety integrity levels range from 1 to 4. If 1 is appropriate, then investing in level 4 is spending much more money than is required. If 4 is necessary, then having a system that operates at safety integrity level of 1 is simply not okay. So trying to have fit for purpose gas and flame detection equipment means that we have enough safety without overburdening the cost. What about proactive methods of identifying leaks? The kinds of things that you can do during a safety walk or during a regular routine maintenance operation. We can go out with a soapy bubble leak test, a universal practice, and go and check for leaks. Or we can use infrared cameras to look for IR specific molecules such as methane. Or we can use portable gas detectors, walk around the site with a portable gas detector, and if it's a multi-gas detector, it can perhaps tell us, number 1, if there's a leak, and number 2, which particular gas is leaking. So there's a number of appropriate techniques that we can use proactively to try and track down leaks and fix them before they cause a problem. Furthermore, there are leak detection technologies that can help us to reactively tell us that there's been a problem. If we have a pipe burst, as in the photograph here, hopefully a fixed gas detector close to that pipe will be able to sound an alarm and tell us reactively that something has gone on. That's not necessarily part of a proactive maintenance routine. It's reacting to a problem, a situation after it's taken place. And there's a number of technologies such as fixed flame detection or fixed gas detection systems that are ideal for that particular purpose. If we ask what's the appropriate gas and flame detection equipment for confined space entry or maintenance operations inside a tank where there may be toxic chemicals or nitrogen and inert asphyxiant gas, well, portable gas detection is ideal to check prior to entry, and area gas detection inside of that confined space would be ideal to have close to the operators, close to the maintenance team during their work inside the confined space. So a mixture of equipment is ideal for confined space entry and maintenance inside confined spaces. And again, the SIL rating of that portable or area gas detection equipment is very, very important to consider and make sure that it is appropriate for the risks that are being taken by the maintenance team. Here are some area gas detectors, very, very typical for use during maintenance operations around toxic or flammable gases, and in particular in confined spaces. And again, if we want to increase the SIL rating of such equipment, we can, for example, use multiple devices. We can use 2 or 3 devices together, and if one of them isn't working, then we rely on the other being working at that particular moment in time to increase the SIL rating, to increase the probability that it's going to be working when we need it to be working. But that can be quite expensive. Buying 2 pieces of equipment is clearly more expensive than buying 1, and buying 3 is an additional cost. So the other way to improve the SIL rating is to buy equipment that has a higher SIL rating. It's one or the other. Both are perfectly valid ways of achieving a good SIL rating for the area gas detection. Buying better equipment or doubling up. And covering what we've just been saying there, the SIL rating of that portable or area gas detection equipment is really quantifying the performance of that equipment, and we've been using some of the appropriate terminology earlier on, the probability of failures on demand, or the percentage of time that it's available to give you the information that you need to operate a safety function, for example, to sound an alarm. When we look at portable gas detection devices such as the one in the photograph here, these kinds of devices are commonly calibrated, tested, bump tested at the beginning of a shift of operation and again at the end of a shift of operation by plugging them into calibration devices, desk-mounted devices. You just drop them into the device. And those calibration events are very, very important to record that that has taken place. A lot of legislation says that the equipment must be calibrated and that the data related to that calibration or testing must be recorded for regulatory purposes. And with such a big data management issue, to demonstrate that an operator is doing the right thing, it can be very helpful to use modern digital platforms such as the Teledyne Gas and Flame Detection GD Cloud, Gas Detection Cloud system for efficient compliance. Looking into that Teledyne GD Cloud, there's a whole host of features that the system is able to offer. I won't go through them all on this particular slide, but I mean, of course, cybersecurity, a major issue, comes as standard with the system, and the systems that Teledyne is offering are compatible with major platform as a service providers, some major cloud computing providers. And some of the intelligent workings within the cloud-based systems can be, for example, alarm prioritization. Absolutely critical. If we have a relatively complex refinery and perhaps multiple alarms going off at any one time, if I've got 3 or 4 alarms going off, 2 or 3 may be quite trivial in comparison to the other 2. Or there may be one alarm that is incredibly important. And if it's getting lost in a noise of 3 or 4 other alarms, then that could be quite a problem. So using significant data management facilities and interpretation of the data to give really important safety information, alarm prioritization, these are all some of the benefits that can be achieved with significant data management systems such as the GD Cloud. On the whole topic of maintenance and fit-for-purpose systems, there's always a question to ask, at what point do I want to upgrade my gas or flame detection system? And I think this is an old Teledyne Oxymat system in the diagram here. If there's anybody operating one of those today, well, perhaps it's time to go and think about a more modern replacement. But again, when we're replacing out-of-date equipment, older equipment, reinvesting, modernizing, then that's a really good time to make sure that you're up to date with the latest products, the latest technologies, understanding what benefits the cloud computing systems can bring. If you're going to spend a lot of money on new equipment, better to do something that's going to be future-proof and up to date with the current standards. Coming on to section 4, we'll have a look at some specific examples of gas and flame detection equipment and SIL safety integrity level certification associated with it. I'm sure a lot of you already know Oldham is one of the brands, one of the businesses within Teledyne gas and flame detection, and the two fixed gas detectors here, I'm sure, are products that are very familiar to a lot of people listening today. The EN 50402 is one of the norms or standards that specify the requirements on the functional safety of gas detection systems. And ultimately it's a product standard, so it's of specific relevance to Oldham within Teledyne gas and flame detection. That standard also refers to various other standards and also refers to how these products should be certified, what kind of testing should be done by Oldham or by Teledyne gas and flame detection to make sure that these products comply with the various different norms and standards. We can't just issue a SIL certificate because we think we'd like to. There are very, very strict testing and certification protocols that must be adhered to claim the safety integrity level of a manufactured device. Similar comments would apply to flame detection equipment, and this is the DF-TV7 series, which, amongst other things, has a very, very good immunity to false alarms. We mentioned earlier on that too many alarms can distract operators. If an alarm is repeatedly a false alarm, then people become a little bit immune to it. So a flame detector that's not being activated by sunlight or some other false alarms is increasingly valuable. And when we think of those elements of the gas and flame detection system, fixed gas detectors, flame detection systems, when we think about those pieces of hardware, they're all often connected into a very, very sophisticated gas and flame detection system across a storage tank terminal, LNG facility or a refinery, whatever the system might be, whatever the operation might be. So a lot of data and information is coming into a controller, such as the one shown here, the MX62. And again, the software that lives inside these kinds of controllers themselves are also an integral part of the overall system. And certification for these controllers is also critical to make sure that the overall system is at an appropriate safety integrity level. The overall system can be thought of as a sum of the component parts. Having said that the overall system is basically a sum of the component parts, the safety integrity level of a total system can never really be better than the safety integrity level of any one particular component within that system. So if our requirement is that the system operates at SIL 2, safety integrity level 2, then we will definitely need individual components within that system to be at safety integrity level 2, or perhaps better. Because as we put more and more and more components together and build more complicated systems, then the overall probability of failure of that system becomes higher. And therefore it may be necessary to have certain pieces of individual equipment within a system rated at SIL level 3 in order for the total system to have a SIL level of 2. So we're moving on to something a little bit different now. We're looking ahead to emerging applications of gas and flame detection equipment. Let's take an example of hydrogen electrolyzers. And the two photographs here, top and bottom, show you a very, very large hydrogen electrolyzer, a 10 megawatt single stack atmospheric pressure electrolyzer from a Sei Hikasei installed in Japan. And the lower photograph, a containerized unit This one is an example from ITM Power, and this is still in their factory prior to shipment. But there's a huge difference between the system at the top and the system at the bottom in terms of scale, but fundamentally in terms of gas and flame detection requirements, a huge number of similarities. We basically have hydrogen being produced, a flammable gas, potentially explosive gas. Also oxygen is produced on the electrolyzer, which we may wish to detect for. And whether it's a big electrolyzer or a small one, the gas detection requirements are fundamentally quite similar. And we're very fortunate that a lot of people close to the industry have given a huge amount of thought to the safety of operating hydrogen electrolyzers. And the international standard 22734 gives very clear and explicit guidance for gas detection requirements in those systems. I've given you some examples from the standard here. I think if you wish to know more, it's a very, very good idea to go and purchase the standard and read it and understand what the implications are as an operator or a builder of these kinds of systems, and how you will need to implement gas detection into those systems for safe system design and operation. That standard makes reference specifically to safety functions and their availability, in addition to gas detection requirements. So the gas detection device would ultimately need to operate a safety function. For example, turn on some ventilation. And that safety function itself, the ventilator, the fan, we would also need to understand that that is operating or available to operate as required. So there needs to be condition monitoring of those ventilation systems to say, yes, this fan is still available, should it be required? Yes, this fan is still available, should be required. So the whole concept of probabilities of failure on demand, or the availability of that safety function, applies to the gas and flame detection system and the safety and function that it may invoke. And these are some of the things that are explained very, very clearly in this particular ISO standard related to hydrogen electrolyzers. Hydrogen and acetylene have the widest flammability ranges of all gases. And that's one of the reasons that through the emerging hydrogen economy and the emergence of hydrogen electrolyzers as a mainstream production route to hydrogen, that people are given so much thought to the development of that standard. Methane, you can see also highlighted on the table here, is of course flammable, and a lot of gas and flame detection equipment exists to detect methane leaks. But you can see quite clearly that the lower explosive limit of hydrogen is less than methane, and the upper explosive limit is significantly more than methane. Acetylene, you can see at the top of the table, is the only gas with a wider range. So therefore, working with hydrogen or hydrogen electrolysis means we really need to pay very, very close attention to the flammability hazards. And when we think about gas detection, we need to think about the sensors that are going to be appropriate. When we think about flame detection for hydrogen, we really need to check that any existing systems that we have in place will be appropriate, or if we're purchasing new systems, that they will be appropriate for use with hydrogen. Why is that? Well, because a hydrogen flame burns to make water, not carbon dioxide and soot and water. It just burns to make water. And a lot of flame detection equipment looks for soot particles or looks for IR signature from CO2. If those soot and CO2 are not present in the hydrogen flame, if we're just looking for water vapor and heat, then we need to have a flame detection system that is working in a very, very different way, in a very, very specialized way. So we might say, oh, well, listen, I've got methane here, and methane is a flammable gas. Now I'm using hydrogen. My existing system should be okay. Well, maybe it's okay, but please don't make that assumption. Please validate that any changes in the flammable gases that you're processing, such as the introduction of hydrogen, please validate that your existing systems will continue to be valid. Thank you so much indeed for your attention. I believe that we do have some time available now for a Q&A session, and I look forward to fielding your questions, and I'm sure that the team at Teledyne will also support me if you start going into some areas where my expertise is running out, but their expertise is still okay. Thank you.
Thank you, Stephen. Next will be a short video from our sponsor, Teledyne Gas and Flame Detection.
Well, thank you, Stephen, for sharing your expertise and insight into this important subject, and Teledyne Gas and Flame Detection for sponsoring today's e-learning session. Again, to remind the audience that a recording of today's event will be online at Petro Online in the next few hours for on-demand access, so you can review key points of interest or share it with your peers and colleagues at your leisure. We have some questions which the audience have submitted during the presentation, and you can still submit questions in the question box, and we can work through these in the Q&A session. For this Q&A session, we'll be joined by Francois Ampe, who is a product manager for Teledyne Oldham Simtronics products worldwide. Francois is a gas and flame product expert in oil and gas, petrochemical, chemical energy, power generation, and food and beverage applications, and will be able to contribute to any equipment-specific questions posed by the audience. So we have one of our first questions let me see where we are. It is, of course, good to have SIL certified gas detectors, but how do you calculate reliability that the detector can actually see the gas? I mean, the OPFD detector is how well it works when it sees the gas, but how do you ensure it will see it?
So, Francois, I'll say a few things. Perhaps you might also have some comments. Locating a fixed gas detector or a mobile gas detector, transportable gas detector close to a maintenance team, or where you wear it on your clothing, the location of a gas detector is really very important. And typically fixed gas detectors are placed in areas of a plant facility where a leak is most likely to happen. For example, over a gas compressor, or over a flange, or over a valve. And in terms of answering the question, how can we be absolutely certain that the gas detector will pick up the leak? Well, perhaps the wind is blowing very strongly in a direction that's blowing the gas away from the detector. Of course, these things are possible. And therefore, the use of multiple detectors around these high-risk areas is really important, so that we can catch the gases as they get moved in different ways. And a combination of gas and flame detection, clearly flame detection is going to pick up a problem after gas detection, after an ignition, but a combination of gas and flame detection is the most secure way to make sure that we're absolutely belt and braces going to see what's going on.
Yeah, Francois, do you have anything to add to that, or has Stephen answered that one?
Yes, fully agree. To help our end customer and the end user, we are doing some audit on site, and just to make it clear with the customer and the people in charge of gas detection, And so that's the best way to provide this this gas detector location.
Okay, thank you, Francois. Another question here. Should the SIL rating always be quoted on the nameplate of the gas detector, and what does this look like?
Thank you. I'll defer to Francois to cover that point, please.
So SIL rated is only, it's not regulatory certification. So it's not right on the firm plate, but we can add some logo if we wish. But you need to refer to the safety manual or the brochure or the technical manual to make it clear with the certification and all the details.
Okay, thank you, Francois. We have another question here that might have quite a lengthy answer, but that may be shorter. Questions: could you outline the compliance differences between a general purpose fixed gas detector and a hazardous area fixed gas detector?
I'll give this a go, Francois, and please do come in with some additional technical details.
So, yes, so the difference between, yes, sorry, go ahead.
Thank you. I'll give it a quick try, and perhaps you can fill in some of the technical details afterwards. There are many gases that we may wish to detect. Some are flammable gases, and some are not. For example, if we're trying to detect an oxygen leak, oxygen itself is not a flammable gas, and it's possible that we're not in an area where flammable gases are being used. In fact, it'd be very good to have separate areas where the oxygen and flammable gases are being present. So if, for example, we are in a location where nitrogen gas also is perhaps a hazard, it's an asphyxiant gas, or oxygen gas is a hazard, and there are no flammable gases present, then we might be able to use a gas detection equipment that is not EX rated, that is not intrinsically safe, that is not rated for a flammable area. On the other hand, if we are detecting hydrogen, or if we're detecting methane, if we're detecting flammable gases, and that's the reason for the gas detection, then of course the device itself will need to be approved for use in a flammable area. It'll have a suitable EX type of rating. Again, personal protective equipment, if you are wearing a gas detector that's simply an oxygen monitor, and you're working in an area where nitrogen is present or oxygen is present and no flammable gases are present, then the type of monitor that you may wish to purchase or specify, or perhaps you're working in a hospital where oxygen is being used but no flammable gases are present, the type of sensor, the personal monitor that you may wish to use may be very, very different to the type of sensor that you may wish to use if you're walking around on an oil refinery, which is clearly a hazardous area with lots of flammable hydrocarbons present. So that would be my quick answer to that question. Maybe Francois also has some additional technical insight.
I think you make it fully clear. So if there is some more question on these topics, let me know. But yes, I think it's. I fully agree.
Thank you both. Question here: How do we decide to use SIL 1, SIL 2, SIL 3, or SIL 4? Can you explain how to calculate that? As a functional safety engineer, we look at that in the procedure to decide and calculate. Any comments on that?
Well, ultimately, there are a lot of safety processes that will need to be worked through when a system is being designed. So we will need to do, for example, a HAZOP, or we might need to do a HAZAN, so a hazard and operability study, or a HAZAN, a hazard analysis. There are various different safety and engineering processes that may need to be followed. And through those processes, certain questions will be asked about how critical is this particular thing to the safety of what's being done here. Are there 6 other things that can prevent an accident, or is this the only way that an accident is going to be prevented? So if there are lots of other ways of detecting a hazard or preventing an accident, then perhaps a SIL rating of 1 would be absolutely fine. If this piece of equipment is the only link in the chain that is going to protect something very, very hazardous, such as a nuclear facility or a refinery, then it needs to have a much higher SIL level. So these kinds of things will be determined through other safety processes, and then the appropriate SIL level will be arrived at. And as I said in my presentation, an appropriate SIL level is really important. If it's a nuclear reactor and it's the primary reactor protection system, then we want to be looking at SIL 3 or SIL 4, and that will cost a lot of money to implement, but that money must be spent to ensure the safety. If, on the other hand, it's a very simple system, the hazards are very low, there are lots of other devices that could also indicate that there's a problem, then perhaps a SIL 1 system is appropriate at significantly less cost. We don't want to, safety is really important, but we don't want to overburden. Everything needs to be proportionate. And the appropriate SIL level will be determined by earlier steps in the safety management processes.
Okay, Francois, do you have anything to add to that, or has Stephen covered that one?
No, it's fully clear. And yes, this safety assessment is coming from the responsive of the site, and which is the responsibility of the owner of the site. So that's how it works.
Okay, thank you. Hydrogen's obviously a hot topic these days. We seem to be getting quite a lot of questions on hydrogen. The question here, would it be better to use pressure drop to detect hydrogen leak on a long pipeline?
I mean, to be very honest, a lot of techniques are appropriate to look for pipeline integrity or the integrity of any pressure system. And absolutely right, rapid fluctuations in pressure can, of course, indicate a leak. Also, if we're thinking about natural gas pipeline integrity, which is ultimately very similar to hydrogen pipeline integrity, we may wish to detect for oxygen and moisture inside the pipeline, because any leak in the pipeline will result in atmospheric air coming in as well as gases leaking out. And if we're permanently looking for oxygen and moisture inside the pipeline, then that's also going to be an indication of a leak. So clearly, gas detection equipment, flame detection equipment looking for leaks, pressure measurement looking for leaks, and other techniques are all very, very important. And in fact, there's another device referred to as an excess flow valve, which is a mechanical restriction, which doesn't just detect the fact that there's a leak, it actually detects a leak through excess flow, through the momentum of the gases that are flowing much faster than they should be if there's a serious pipeline rupture, and it automatically closes a valve mechanically. So there's no need for a DCS control system, there's no need to rely on sophisticated process control networks or operator intervention. There are also mechanical protection devices that can protect natural gas and hydrogen pipelines from catastrophic rupture and block a leak as soon as possible. So I think an appropriate range of detection and prevention mechanisms, whether it's a mechanical device that's automatic or whether it's a pressure sensor or a gas detection system that's going to come into a DCS system and then invoke some kind of safety function such as shutting an automated control valve or whatever, a number of systems must be considered, and I'm sure more than one system will be implemented for major hydrogen transmission and major natural gas transmission pipelines, because ultimately hydrogen and natural gas transmission pipelines will be relatively similar. And for some point in time, hydrogen will be blended into natural gas systems as well. So we have to look at the similarities across both systems. But frankly speaking, a range of systems must be relied upon. Pressure measurement is one of those, and there are many others.
Okay, thank you. Another question on hydrogen. What is the best technology for hydrogen gas detection? Is there a favored technology here?
I'm going to leave that one to François. François, please.
Yes, Steve. So to detect hydrogen, the easiest way is to use cat bead detectors, which is really easy when you have a standard environment, when you have O2 as a 20.9% volume, and you will be able to detect any hydrogen leak. And depending on the environment, if you are indoor, outdoor, cat bead will be fine, and that's the most popular, I would say, technology.
Okay, thank you, Francois. We have another question here. Do all fixed flammable gas detectors have to be EX rated? I see a number of manufacturers offering more general purpose products without an EX rating, but are promoted as safe area gas detection, such as boiler rooms. I presume that just depends on the rating of the area, but any comments on that?
I answered a similar question earlier. Maybe Francois would like to give his thoughts on this one.
Yes, so yes, we have EX rated devices, because yes, we are facing a lot of requests on this environment to let us propose the whole range on the project with gas detection, flame, open pass, and controller. So for sure, we are able to quote and propose such flame detectors with EX rated, and for sure we are able to propose all the flame. You know, as we have to define the right technology on the flame detection. Flame detection is related with what is burning and which flame we will face, and what technology will be able to detect it. So, and yes, we are able to define all these products together with the EX rated.
Okay, thank you, Francois. Question here: how do you account that in all instances the gas will not be able to get to the head itself? You know, this may be a question about where do you site your detectors, but can you calculate the probability that the gas will get to the head when there is an accidental release?
I answered a similar question earlier. I'll leave this one to Francois this time.
Mm-hmm. Thank you, Steve. So yes, it's not an easy question, because yes, you can manage calculation. You can use software to be able to have a scenario, you know, and to use it on the software. But yes, the gas need to be on the sensor head to be detected. And as I heard the answer from Steve before, if there is some wind coming or big airflow coming on the indoor area, for example, it's not easy to say that we are 100% sure that the detection will be okay. So that's always a balance, I would say. If you want to be sure, you need to put a lot of detector. But yes, for sure, the budget will be higher. So it's always a balance to find the best solution, and that's how we are doing when during audit. And we have some people in our engineering application engineering team who are able to define this location for you.
One of the things that I might add is that ultimately all gases will diffuse, and convection currents such as wind will mix gases around. That's ultimately what will happen. If you leave gases in a bottle long enough, Brownian motion will mix them up. But gases do tend to rise or fall depending on their characteristics when they leak. So, for example, if we have a very cold gas, if we have a cold leak of oxygen or a cold leak of nitrogen, because it's a very, very cold gas, its density will be high and it will sink. Ultimately, as it warms up, it will rise again. Hydrogen is a very light gas, and typically it's emitted upwards rather than downwards. Methane, again, we can go through a long list of gases and say whether they're lighter or heavier than air. And when placing a fixed gas detector, consideration of the most likely gas that's going to leak, or the gas that you're actually looking for in terms of a leak, the main hazard, may say whether the detector should be fixed above or below where the leak point is going to be, or you fix one sensor that's looking for hydrogen above and another sensor that's looking for a different gas below. So these are also, the densities, the relative densities of the gases that are leaking, which is driven by the molecular weight of the gas, and also the temperature, are also relevant considerations for the optimal siting of the fixed gas detection systems.
For sure, and fully agree. And all the environmental parameters need to be taken into account. So pressure, humidity, temperature, flow, and the expected scenario. If there is some leak coming, if it's only a 2-liter bottle of hydrogen which can leak, for sure you will face some issue, but the expected disease is not so high versus a big tank of 20,000 liters with a high pressure. It's always, as I said, a balance to find the right location, the right number of detector, and to get the right safety according to the specification of the end user. That's always a balance, I would say.
Okay, thank you. There's quite a few other questions relating to the same sort of topic, which I think we've pretty much covered in your answers to some other questions. So there's one here that does say, how do you take into account potential cross-contamination from other gases which may be in the area? How might that affect a SIL rating?
I'll leave that one for Francois, a deeply technical question.
Yes. So yes, it's really not easy because, for example, if you want to catch some leak of methane, you can use both IR technology or CatB technology. And if you have some silicone, for example, on the location you want to use your detector, be careful because CatB can be poisoned by silicone, and IR is not. So that's why when you have some to define the technology and the location of your detector, it's always it needs to be clarified by the end user, the guy who are doing their work on site, and how they are using their gas, the process and the habits on site. And it's always a lot of discussion and clarification we have to do, and to make this kind of audit as clear as possible to define the right technology. But yes, we can face a lot of issues with O2 detection, for example, with some gases which can poison the O2 detection. CatB can be poison also, and when you have some mixture of gases, it's always not easy to clarify all technology, and so if you need some help, do not hesitate to ask to some sales engineer we have, or we have some application engineer also and chemist to help with some not easy application, I would say.
And the last thing I would add there is, if in doubt, installing 2 gas detectors for the same gas with 2 different technologies can be one of the best ways around the problem. Because if one of them becomes damaged by cross-contamination, by sensitivities, there is still a chance that the other one might be working. If you're going to install 2 gas detectors with exactly the same technology, there's always a risk that both of them will go down at the same time and you're left with nothing. So if you have the budget and the need to install multiple detectors, it's always worth thinking about different technologies in those detectors, even if you're looking for the same gas.
Well, thank you very much, Stephen. That's a very valid and sensible point. And unfortunately, we've now come to the end of our live session. So thank you again to Stephen for your presentation and answers to the audience questions together with Francois. Any questions which we did not manage to cover in the available time will be answered by email shortly. Thank you to our audience today for attending this e-learning session brought to you by Petro Industry News and sponsored by Teledyne Gas and Flame Detection. Also, please feel free to request your certificate of attendance, which you can see will be available on your screen for download. Look out for the next e-learning sessions in 2022 and beyond by visiting petroonline.com and click the e-learning tab at the top of the page, where you can also see details of future events, but you can also access all the recordings of all the past e-learning events, and there are quite a lot of very good ones in there. Until then, have a good day. From me, Stephen from SBH4 Consulting, Francois from Teledyne Gas and Flame Detection, and all the Petro Industry News team. Thank you, stay safe, and until the next time, goodbye.
Bye-bye.